Okay, so today we are going to talk about small sample. Gotta get my pen working. Confidence intervals. And so we have to have a little bit of background on what's going on, okay? So small sample means that you have less than or equal to 30 in the sample. Okay, and the central limit theorem says that the sampling distribution mean, which we've talked about a few times in past lectures, and proportion, right, both of them, are normally distributed. But the problem is that when n is less than or equal to 30, they're not perfectly normally distributed. They're somewhat normally distributed. So we have to have a variation of the normal curve, and that variation is called the student's, the student's t distribution. And it works just like the normal distribution in that it looks like the normally distributed random variables. It's centered around 0. It has standard deviations just like the normal distribution. However, the empirical rule of the, mu plus or minus sigma basically creates a probability. Let's write it like this. The probability of being in beside there is 95%. It's not even 95%. Sorry. It is 68%. That being within 2 standard deviations is 95%, and being within 3 standard deviations is 99.7%. In the student's t, this kind of rule does not apply, and so we have different markers here in order to get the 0.95, again with the tail 0.025. And those tails, these markers, are determined by what we call the degrees of freedom in the student's t distribution. So there's a definition for degrees of freedom. So degrees of freedom is always equal to n minus 1 in the t distribution. So example, if n is 25, the degrees of freedom equals 24. So it's just always 1 less than the sample size. And this comes to play so that we can label how we deal with that t distribution. So if we're here in n equal 25, degree of freedom equal 24, and we want to kind of look at 95% in the middle, which would indicate a 0.025 here and a 0.025 here, we want the t value at 0.025 with 24 degrees of freedom. And the way we do that is we go to our t-tables. So sometimes t-tables look like this. You can see that here's the area in the distribution. Sometimes it looks like this, where it gives you the confidence level and it tells you the right tail probability so that you can see, let me zoom in a little bit, so that you can see it tells you how much is in the tail. So that from this example, we're looking at a 0.025 and a 0.025. So this is 0.95, though you're just looking at the tail probability, which is a little different than how the z-tables work. So if you want this t-value right there, you go down into your table. Let me erase this. You go down into your t-table and you go to 24 degrees of freedom right here. And 24 degrees of freedom at 0.025, so you match them up, and it's 2.064. So the t-value would be 2.064. Same thing if you're on that other T. It doesn't matter which T chart you're looking at. So if you're looking there and you have your right tail amount of 0.025 and you go down to 24 degrees of freedom, you can see that it is right there at the bottom of the screen, the 2.064. So no matter what t-table you look at, it's going to give you the same t-value. So this table is different because the t-values are on the inside and the area is up here, versus the z-table had the values on the outside and the probabilities in the middle. So it's a little bit different of a table than the z-table, but after you master the z-table, the t-table is way easier to deal with. Okay, so that's how we find the t.025 with 24 degrees of freedom. If we do another example and we want to look at, let's say, a 90% confidence interval, therefore we know that this is 1 minus alpha, right? 1 minus alpha is 0.90, therefore alpha is 0.10, so alpha over 2 is 0.05. Okay, so this amount here is 0.05 and this amount here is 0.05. Therefore, what I'm looking for is t 0.05, and let's just say in this example, n is 18. Therefore, my degrees of freedom will be 17. And that value, if I go and look at a table, is I want 0.05 with 17 degrees of freedom. So I'm here at 0.05 with 17 degrees of freedom. We can see that the score is the 1.740. Again, it corresponds to a 90%. If you go to this one, it's 0.05. The right tail amount's 0.05, 17 degrees of freedom, you can see it's 1.740. So no matter which table you have, depending upon your textbook, it's 1.740. So that amount, that number is 1.740. So if we're building a small size confidence interval, so let's do an example here. Okay, here's my example. A brand of margarine, not a very exciting example with margarine involved, but a brand of margarine was determined was examined first. Examined to determine the level of fatty acid. Okay. A sample of 6 products produced the following. And this is grams of fat. Okay, and the data is 16.8, 17.2, 16.9, 16.5, 17.1, and 17.3. So those are my 6, okay? The directions say construct a 95% confidence interval on the true average of fatty acid. So just like in large sample confidence intervals, we have to kind of do a little bit of work beforehand. So we'll start the solution now. The first thing you need to do is you need to determine the sample size. The sample size is not 5. The sample size is 1, 2, 3, 4, 5, 6, or it says up there 6. So N is 6 because that means small sample. We know that we have a degree of freedom measure that is 5. Okay, so to construct a 95% confidence interval around the true average, we're going to take X bar and we're going to add and subtract that T statistic at the alpha over 2 level with some degree of freedom, we already know it to be 5, times the standard deviation over the square root of n. So nothing changed in our confidence interval except the statistic to build the confidence interval, or this t value, which is just transferring basically x bar into a standard curve, in this case the student's t curve. Okay, so from this data right here, we need to find the mean, right? So that's kind of a separate thing. X bar, you can either add them all up and divide by n, and we also are going to need the standard deviation, or s. In this case, we're going to take s and plug it in for our standard deviation because we don't have the population standard deviation. It's coming from a sample. That's why we have a degree of freedom of taking 1 away, because we're going to estimate sigma with s. We're going to do one estimation. That's why we take 1 away for our degrees of freedom. And s, we know, is the sum of x minus x bar squared all over n minus 1. So you can do those calculations, which I know you have done before, or you can go here, and it doesn't really matter what this is a Northern New Mexico class that I teach. It doesn't matter which one you teach, just go to StatCrunch. If you're in UNM's class, go to UNM. If you're at Northern New Mexico or Santa Fe, I teach at a lot of places. So it doesn't matter which one you're in, you all have StatCrunch, okay? So you go to data sets from the textbook. And in this case, you don't need the data sets from the textbook, you just enter your data in. So it's 16.8. Right, so I'm just entering the data that is from that right here, 16.8, 17.2, 16. Okay, I'm just entering those in to StatCrunch. So 16.8, 17.2, 16.9. I have a 16.5, a 17.1. and a 17.3. So I've entered it in. Notice I have all 6 of my data points in there. Now I can go to stat and I can go to summary stats. I'm going to do it of the column. I'm going to do it of var1. I definitely want the mean. I think if I hit shift, I can get the mean and the standard deviation. So all three of them, it doesn't matter. And I go to compute. And you can see that the mean is this and the standard deviation is this. So I'm going to take those numbers, 16.97, and actually I'll probably take it out more decimal places just to be really clear. 16.9667 and 0.2944 are what I'm going to use in my example. So I know that that x bar is 16.9667. I'm going to add and subtract some t statistic that I'm going to fill in, and I'm going to multiply it by 2.2944 divided by the square root of 6. Now the issue is, what am I going to put right there? So the way I'm going to do it is I'm going to go back out to my tables, and I want 0.025 in the tail, right? 0.25 right here, because I'm one of 95% confidence interval, therefore that's 0.025. I'm going to bound it like that. So I go to 0.025 with 5 degrees of freedom, and it's this number right here, 2.571. So the number that I care about is 2.571, and I got that from the table. Then I'm going to proceed to do the calculations, and I get 16.9667 plus or minus, and this is, when I do that calculation, 0.3090. This is the error, meaning, which is also the same as the width of half the confidence interval. From a kind of graphical perspective, right, this confidence interval is centered around 16.9667, and the bounds are what I'm trying to find. This width right here is 0.3090, and this width right here is 0.3090. So I'm going to find those by adding and subtracting. So 16.9667 take away 0.3090 equals 16. Let me erase it and write it better. Is 16.6577, and when I add it, that width in, I get 17.2757. Therefore, my confidence interval runs between 16.6577 and 17.2757. And I can say that we are 95% confident that the true average amount of fatty acid in the margarine is between 16.6577 and 17.2757. And again, this confidence interval was only created off of a sample of 6. So that's a pretty kind of powerful tool. You can have a pretty small sample as long as that sample is good, and you can bound a population estimate around it. Now there's a chance that we had kind of a bunk sample of 6 margarines, and that really, if you sampled more margarines, the mean would fall outside in sort of this area? Well, that's the 5% risk we take. There's a 5% chance that the average is outside the bounds. And that's just what we take. This is what we call a type 1 error, which we'll talk a lot more about in the class. But that's how you create a small sample confidence interval around the population mean. If you wanted to create a small sample confidence interval around the population proportion, it would just be p hat plus or minus that t statistic, just like we found, alpha over 2 with some degrees of freedom. And in this case, it's going to be the p hat q hat over n. So this is a small size sample, a small size confidence interval around a proportion. So it's the same theory, it's just what your different estimate is from. So use this information. You can do your homework on confidence intervals now, and that's all we really talk about on confidence intervals, and we'll move on to the next topic.